Hey, what's up? It's Sergei, and I'm here with
Mariam.
And we're here in Cleopatra's Treasures, vintage clothing store just off the strip in beautiful Las Vegas. So why don't you tell us a bit about it?
So Cleopatra's Treasures is one of the only locally owned buy-sell trade clothing stores in Las Vegas. It specializes in vintage and designer resale. Now I got into it probably when I was under 20, and so I had my mom co-sign, and it was pretty much a miracle at that time. So started it now here 4 years later. We have another location.
Is this dress vintage?
No, this dress is not vintage, but it is designer.
It's designer?
Yes.
Alright, very cool. So why don't you tell us a bit about the topics we were talking about in pre-production?
So pretty much since last year, I really got into the Large Hadron Collider, dark matter, and CERN, and especially the aspects of physics that involve that type of those topics.
So like cutting edge modern physics. Okay, that's really cool. So just want to point that out. Like anyone can get into this stuff. Like we talk about it in the news all the time, and you shouldn't be like scared of it. I think it's super cool when people who like do something completely out of science, like fashion, can like get into this and just get into it. So in particular, what like really drew your attention from like maybe the last story that just comes to mind?
So the last story that comes to mind would probably be something that was not covered in necessarily the media and popular media. It was more something that was people who are interested in these topics really research, and it was just the fire that happened at CERN, and CERN is in Geneva, Switzerland, which occurred in between November 13th and 14th of last year.
I didn't even hear about this. So this goes to show like it's hard to stay on top of this. So there's a fire at CERN?
Yes, there was a fire, and it was shut down for about 2 weeks. They didn't want to say anything about it because it was an intern who was operating it and thought the machine was off, but it really wasn't, and there was really no one around when the incident happened.
This is like super embarrassing. Like the intern's probably watching, and he's like, "Oh my god, they're talking about me." So I heard about like when they opened, they had a huge shutdown for like a year, but I didn't know that they had this minor shutdown.
Well, it was recent because right now they're in the second part. CERN and Large Hadron Collider originally started in the 1960s. So now we're in 2016, and there's just been so much more going on with it because they're in phase 2. The first phase was between 2010 and 2012, and now we're in 2016, so they're in the second phase. This fire just occurred last year, so they were shut down and delayed a little bit on their research because they are trying to open a portal to a parallel dimension.
Okay, I'm a little freaked out by this portal. I haven't heard about that either, nor the fire. So for people watching at home, CERN is, or the Large Hadron Collider is the particle collider that they have in Switzerland/France, because it's so big it basically goes in 2 countries. And so they basically opened a new experiment in what year? Do you even know? I don't even know. Like 2014, I think.
Yeah.
So they opened in 2014, and so the basic idea with a particle collider is you take a bunch of particles, get them moving really quickly in a circle, and then get another bunch of particles moving in the opposite direction, and then they collide, and then when they collide they make a bunch of other particles, and you can study what comes out. And so the idea is the more energy you can give to those particles that are circling around and before they collide, the more new and interesting kinds of particles will come out. And so each of these upgrades that Miriam's talking about has to do with increasing how much energy you're giving to those particles. So how excited were you when they found the Higgs?
I was pretty excited. I was like, I can't believe that happened. I was just like, I'm kind of confused on really what a Higgs is. I'm not really a specialist in that, so maybe you could tell me a little bit what a Higgs is. I don't know. So
just full disclosure, I'm not a Higgs specialist, but the basic idea is this. So all particles have a mass, unless they're massless, okay? And the way you can interpret mass is how they interact with this Higgs particle. So the way to think of it, think of like the Higgs particle as like a sea of people, okay? And think of your mass as how hard it is to walk through this sea of people. So if I try and walk through a bunch of people, they're just gonna get out of the way. They're like, oh, there's a physicist coming through, I don't want to talk to him. But if, say, like George Clooney walked by, everyone's gonna want to try and like talk to George Clooney and get an autograph. And so they're gonna start swarming around George. And so he's gonna find it really fucking hard to walk through, because there's gonna be all these like people like, George, I want your autograph. And so they're basically gonna get in the way. And so George is gonna have a big mass versus I'm gonna have a small mass.
Okay. So that's why probably the scientists were so shocked, because they were saying that it started at, which if I'm correct, I think it was 4 TeV, and it at per beam accelerating, so that would be 8, and then it went up to 6.5, so it almost went up by 30 to 40%, but the mass did not increase.
So, okay, so let's think of it like this, okay? Imagine you're trying to figure out, or trying to create new particles, right? Think of it like you're shooting one ball and I'm shooting another ball, okay? And the more our combined energy is, the higher their combined energy, the more new kinds of particles will get created. Because, so what's your favorite equation I'm assuming this is your favorite equation.
Yes.
Like, what's your favorite physics equation?
I don't know.
Okay, it's probably like the most famous one. So E equals mc squared.
Okay.
Right, Einstein came up with E equals mc squared. You've seen this. There's probably like 8 shirts in here that like have that written on it. So what does that mean? It's saying that the energy equals mass times the speed of light squared. Okay, so what that's basically saying is energy and mass are basically equivalent. They're the same thing. So if we want to create a particle with energy m, with mass m, then how much energy do we need? Well, we need E divided by c squared. Okay? So the Higgs is going to have a certain mass. That's just a property that the Higgs has in the universe. And so if we want to be able to create them with this particle collider, we're going to need the mass of the Higgs times c squared amount of energy. And so if we're not providing enough energy, so my particles I'm shooting and the particles you're shooting, so if the amount of energy you have is too small, then you just won't be creating any Higgses. And so we slowly have to increase the energy until we reach that special energy that we can start producing them.
Okay, so I have another question for you too. So if we use an electromagnetic field to power the machine, how does what you're seeing correspond to that?
So let's see. Let's think of it this way, okay? So we're accelerating charged particles, okay? So charged particles can have forces applied on them in 2 ways. You can either apply an electric force or a magnetic force, okay? So first let's...
Can be both.
They can be both.
Okay.
So let's talk about like both of them separately and how they're different. So if I have a charged particle, so say like a proton. So a proton is a positively charged particle that lives in atoms. Okay. So if I have a proton right here, if I apply an electric field pointing in this direction, then the proton is going to feel a force in that same direction as the electric field. Okay. So apply a force this way, protons are going to go that way. That's one way to start accelerating the particles. So we just put some protons there, we apply an electric field, they start going this way. That's good, we got it going in a straight line. Now we got to get it going in a circle. Okay, so how do we get things going around in a circle? Well, then we need magnetic fields. So you're probably familiar with magnetic fields from your fridge magnets that you have at home. You have fridge magnets?
Yes.
I have one as well. There's one with like a little frog. So the point is, unlike the electric field, the magnetic field, the force isn't going to be in the direction of the magnetic field. It's actually going to be perpendicular.
Okay.
And the other thing is we need the particle to actually be moving. Okay, so now we'll do like a little experiment. So you take your right hand. Okay, so it's called the right hand rule. That's what we call it in like introductory physics class. Okay. So you put your thumb, okay, it's going to be the direction that the proton is moving. Okay, so let's say it's going this way. So, alright. We put our thumb that way.
So you're going
Okay. And now, let's say the magnetic field is pointing downwards. Okay. So then we put our other fingers pointing in the direction of where the field is pointing. Okay. So the proton's going this way. The magnetic field is going down. So then the right hand tells us where the force that the proton feels is. So it's coming out from the palm. So it's coming out like this. Okay. So that means the proton's going this way, but it feels a force that way. Okay.
two directions.
So in a direction perpendicular. So it's moving this way, but it starts to move that way. So now let's think about what the motion is going to look like. So it moves this way a bit, but then it feels a force this way. So it starts going a bit in this direction. So now, where's the velocity going to be pointing? It's going to be tilted a bit, like maybe like that. And then where's the force field? This way. Then it's going to start moving a bit like this. Force this way.
Reading the circle.
And so it's going to start moving around in a circle. So the way that you get these particles moving in a circle is you turn an electric field on that gets them moving in a straight line. Once they're moving in a straight line, you turn on a magnetic field and then they start going around the circle. And how big is the circle? Well, it depends on how strong the magnetic field is and how fast they're moving. So let's think of it like this. When they started building these accelerators, okay, in I think like the 30s, okay, these things were really small, right? You could just build one of these and put it on a table in a lab somewhere, like they'd be like this big. Now, it turns out that the amount of energy that the particles have goes like the size of the circle that they're traversing. So remember, we said we want to create new particles. New particles are at higher energies. So higher energies means that the circles that the particles have to be going in have to be bigger and bigger. So the particles are going around in a circle. And the larger circle that they're going in, the more energy they have. And so if we want to create new particles that have higher mass, hence we need a higher energy, hence the particles that we're colliding have to be going in bigger and bigger circles. Hence, now particle colliders, unlike the first cyclotron in like the 1930s in Berkeley, now they have to be huge, like 40-kilometer diameter rings that go from like France to Switzerland and back again. So did you know where did you know where they wanted to build a collider in the United States before CERN? Before this experiment at CERN?
In the United States?
Yeah.
Where?
This is probably like we should barely remember this because we're not that old.
No, I have no idea. I know they have 3 underground, but I don't know.
So they wanted to build one in Texas, which would have actually been bigger than CERN. And they actually dug up the hole. So they dug the tunnel underground.
What prevented them?
They ran out of money.
Okay.
The Clinton Congress
Who
canceled it.
I don't know who funds them. Do you?
So
I know it's the top 100 scientists, but it's not government.
So it is ultimately all government funded. Because there's basically like no industrial applications for this. It's kind of anything that would come out of it would kind of be like tangential, and so most of it is all government funded.
Now it is. Before it was all families. Like the top elite families.
No, that's a good question actually.
I think it was.
I would probably bet that it was always government funded because the amount of like most grants always come from like NSF. The National Science Foundation, or like NASA, or because think of it like this, right? So you want to start this big experiment that has like 1,000 scientists or 5,000 scientists. So all those scientists are getting their own funding from their own government, and then they kind of like doing it all together. And I can't even imagine how they organize these kinds of collaborations because you're talking thousands of people and like between different countries. So like they have to decide, okay, which country is going to host the thing. So there's actually a huge economic impact because imagine you build this huge lab that has 1,000 scientists. They all have to eat. They all have to live someplace. So it's like actually a huge boon on the economy. And I feel that when we're trying to sell these huge science projects to the public, we don't do a good job of explaining that because people think, okay, well, we're funding this project, it costs like so many hundreds of millions of dollars or whatever, but who's that paying for? It's paying for a bunch of scientists that instead of good paying jobs. And so we should actually do that to attract people to our country. So every week we do a book review. So tell YouTube about a book that you've read recently that you thought was really good.
So the most recent book that I read is going to be the Large Hadron Collider, and it's Unraveling the Mysteries of the Universe. It is by...
What is this nerdy book that I've never heard of?
Well, because it all has to do with the Large Hadron Collider and how the particles are accelerating and how fast they have to go and how it's changed over the 40 or more than 40 years that it's been established, and how other countries are also, each one is different and how they're similar in the same way, but if they're all combined, then they can be an enormous amount of energy that's being used.
This sounds good. I'm going to check it out. Link below.